In May 1993, at the National Center for Atmospheric Research in Colorado, the world's most advanced climate simulations began to return inconsistent, chaotic data. This data coverage map reveals the scale of the simulations. Scientists were running the MM5 global atmospheric and oceanic circulation codes, attempting to model the Earth's entire climate system in high resolution. The engine behind these models was the Cray 3, a monolithic black cube known as the Graywolf. To maintain its operating temperature, the entire processor assembly was submerged in a violently boiling bath of clear liquid fluorocarbon. During these data-intensive runs, the researchers detected a pattern of systematic mathematical failure. The supercomputer was silently producing incorrect results. A physical flaw buried deep within the machine's architecture was corrupting global climate models. The machine built to push the boundaries of human knowledge was undermining the very data it was designed to create. Seymour Cray had spent decades defining the upper limits of the supercomputing industry. His previous designs set the standards for raw processing speed that the rest of the world struggled to match. Global macro systems relied on this hardware. In the final years of the Cold War, the National Security Agency required Cray's vector architecture to manage the intense demands of cryptanalysis and signals intelligence. By the late 80s, the intelligence community required speeds that standard commodity silicon could no longer physically deliver. The material limits of traditional semiconductors had become a bottleneck for national security. Gallium arsenide was the theoretical solution. This exotic semiconductor material offered superior electron mobility and high radiation resistance, promising performance levels far beyond the reach of silicon. The Cray 3 was a billion-dollar bet to abandon the silicon standard. It was an attempt to outsmart established material physics by building an entire supercomputing dynasty on a new, unproven foundation. At these frequencies, the primary constraint on architecture is the time it takes an electrical signal to travel down a wire at the speed of light. To achieve a 2-nanosecond clock cycle, Seymour Cray mandated that no single wire within the machine exceed 12 inches in length. Meeting that requirement meant packing 1,000 bare gallium arsenide dies into space just 1 inch square. This microscopic integrated circuit path shows the density required. Engineers routed the data through a 69-layer circuit board to maintain the necessary proximity between components. Because traditional soldering was too large for the scale, the entire microscopic architecture was welded together using ultrasonic gold wire bonding. To defeat the speed of light, the machine was condensed into a claustrophobic maze of unprecedented mechanical density. That density created a lethal thermal footprint. Without active intervention, the logic modules would reach temperatures high enough to destroy themselves the moment the system booted. To prevent this, the machine relied on a massive life support system that pumped fluorinert coolant directly over the bare semiconductor dies. While the computer itself was small, its infrastructure was massive. It required a municipal-scale power grid providing 90 kilowatts of continuous electricity. The system generated 310,000 BTUs of heat every hour, the thermal equivalent of heating 6 average homes, requiring industrial refrigeration to keep the hardware stable. The push to make the computer small resulted in an industrial-scale chemical and electrical plant designed solely to keep the processors from melting. Beyond the cooling challenges, the material itself was difficult to manage. Gallium arsenide is brittle, toxic, and resists the reliable manufacturing processes used for silicon. Success in the hardware industry is dictated by fabrication yield, the ratio of functional chips produced on a single wafer. In 1990, Cray's internal foundry was achieving a 15% yield. 85% of their custom wafers were coming off the line as defective waste. These manufacturing failures drained the company's capital and pushed delivery dates back by years, alienating the defense contractors who had funded the project. While gallium arsenide stalled in the cleanroom, cheap commodity silicon was scaling upward through the compounding efficiency of Moore's law. Superior physics cannot save a technology that the industry is unable to manufacture at scale. The errors in the NCAR climate models originated from the physical fragility of the exotic hardware. The code was merely the mechanism that uncovered the buried hardware flaw. The defect was baked into the sub-micron logic gates responsible for the machine's new square root instructions. The corruption was microscopic and intermittent. occurring in exactly 1 out of every 64,000 mathematical operations. Engineers eventually patched the error by rewriting the system's compilers. They commanded the supercomputer to ignore its own square root hardware and default to slower, software-based approximations. As the Cold War ended, the market for custom vector supercomputers evaporated. Major contracts, including a $30 million order from Lawrence Livermore, were canceled in favor of massively parallel silicon processors. The microscopic hardware bug mirrored the company's collapse. The Cray 3 remains a relic of an ambitious, flawed design, a reminder that the modern world is built on the reliable, high-yield silicon atom.